Pre-Calculus, Chapter 1, Functions and Graphs, Lesson 1.6, Transformations of Functions. In this lesson, we're going to start by going over the parent graphs or the basic shapes of very popular graphs that we need to know by heart and their characteristics. These graphs are going to include these 7. F of x equal to c, which is the constant graph. F of x equal to x, which is the linear graph. F of x equal to the absolute value of x graph. F of x equal to x squared, the quadratic. F of x equal to the square root of x. F of x equal to x cubed, or the cubic. And f of x equal to the cube root of x. It is essential to know these characteristics of the graphs of these functions. And when we're talking about characteristics, we're referring to the domain and range of the graphs, the intervals of increase, decrease, and constant for each of the graphs, and also any symmetry that each of these graphs might contain, either even, odd, or neither. The first one we're going to look at here is going to be the constant graph. You'll notice here that the constant graph, if I put it right there, is just our horizontal line because it is just the constant value of the y value for any x. So if we look at this, it doesn't matter what the x value is, we're automatically going to get the y value out that we have given as c. So for domain and range, we'll notice here that the domain of this graph, remember domain is how far left to how far right. Well, since this graph covers the entire x-axis, our domain will be all real numbers, or another way of saying negative infinity to positive infinity. Range, on the other hand, for this graph is, remember, range is the y values. Since the constant graph only exists at one y value, the range of the graph will always be whatever is that constant c we have set it at. So like in this case, since I have c equal to 1, the range here would just be the value 1. You'll also notice for the intervals of increase, decrease, and constant, well, this graph is staying constant all the way from the left to the right. So in this case, we have no intervals of increase or decrease, and we're just remaining constant for all real numbers. The cool thing about the constant graph, though, is that it does have symmetry. If you notice that our options for symmetry are even, odd, or neither. And remember, for it to be an even function, the left side of the graph must be able to fold over the y-axis and match up perfectly with the right side. You'll note here that we're able to do this. And so the constant graph does have that y-axis symmetry, making it an even function. The next graph we're going to talk about here is the linear graph, or f of x equal to x. We'll note here that we've seen this graph before. For domain, you'll note here that our linear graph goes all the way to the left as it goes down and all the way to the right as it goes up. And so our domain here is going to be all real numbers, or negative infinity to positive infinity. Range will be very similar because on the y-axis, the linear function can go all the way down and all the way up. So range will also be all real numbers. For intervals of increase, remember, as we move left to right, we are increasing the entire time. So the interval of increase here will be all real numbers as well. There is no interval of decrease for the linear graph. For a graph to have odd symmetry, we must have rotational symmetry about the origin. Please note that if we were to take the bottom left the bottom left quadrant of the linear function and rotate it about the origin, it would match up perfectly with the top right quadrant of the graph. This means here that it has that rotational symmetry, and so this is an odd function. If you also think about in terms of exponents, this is like x to the first power. Well, since it has an odd exponent only, then that means it's going to be an odd graph. The next graph we want to talk about is the absolute value function. In this case, the absolute value function looks like our V shape. The reason why here is, remember, absolute value always makes a number positive when we're evaluating it. So it's kind of like we took the linear function, but for any negative x value, it just got reflected up above the x-axis, creating that V shape. When we're talking about domain here of the absolute value graph, you'll again note that we are able to go all the way to the left and all the way to the right. So the domain here is going to be all real numbers for the absolute value graph. Range, on the other hand, is going to be a little bit different. The furthest we can go down the y-axis is here at the origin, or 0. We can go all the way up on the y-axis as much as we want. So that makes the range going from 0 with a bracket all the way up to infinity. You'll also notice that the intervals of increase and decrease are a little bit different on this one. As we move left to right, imagine yourself kind of riding a roller coaster. Well, our roller coaster goes down from negative infinity all the way to 0, but then at 0, we begin to increase. So the interval of decrease here would be from negative infinity to 0, all in parentheses, and then our interval of increase would be from 0 to infinity as we're going to the right. If we think about symmetry for this graph, please note that we are able to take the left side of the graph and fold it over perfectly to match the right side of the graph, making this an even function. So in either direction on the x-axis, we will always get the exact same y value. So for like 2 and negative 2, the y value is both at 2. Very similar to the absolute value graph is the quadratic. It has a lot of similar characteristics. Where the absolute value graph was our V shape, our quadratic is this parabola, or that U. Again, the lowest point on it is that origin at 0, 0. For domain of the quadratic graph, you'll notice that this graph still goes all the way to the left and all the way to the right, giving us a domain of all real numbers. But again, like for the absolute value graph, the range is going to be a little bit different, because since the furthest we can go down is the origin, but we can go all the way up to infinity. So our range here would be from 0 to infinity, with a bracket on that 0 since it exists there. Another cool thing about the quadratic graph is going to be the intervals of increase, decrease. Again, if we imagine ourselves on this roller coaster, as we go left to right, we're decreasing from negative infinity all the way to 0, but then at that origin, we start increasing. So the interval of decrease will be from negative infinity to 0, but then our interval of increase will be from 0 to infinity. Just like the absolute value graph, which had that y-axis symmetry, the quadratic also has that y-axis symmetry, making this an even graph. Another way of proving that is if we look at the actual equation, well, since it only contains even exponents, that also makes it an even graph. So any any matching x value and its opposite, so for example 1 and negative 1, will have a similar y value, going up and over in both directions in the same way. The next graph we're going to talk about is the opposite of the quadratic, or in this case, the square root. You'll kind of notice that the square root graph kind of looks like the parabola turned on its side, but missing its bottom half. That's because the square root graph is for square roots, which we can only take the square roots of positive numbers. So in this case, when we're talking about the domain of the square root graph, the square root graph has a domain starting at 0 with a bracket going all the way to the right to positive infinity. Its range is also very similar because the range also starts at 0, and even though it kind of looks like it's leveling out, it's still increasing here as we go. So the range is also going to be that 0 to infinity. For intervals of increase, decrease, and constant, we'll note here that as you follow my arrow, you'll notice that we're increasing the entire time. So even though we're increasing the entire time, it's not going to be all real numbers for the interval of increase because the domain is only from 0 to infinity, which matches our interval of increase. So no decreasing, no constant, but just increasing from 0 to infinity. And what about symmetry on this one? You'll note that there is no other side to this graph that we can do any kind of reflection with. So this is an example of a graph that has no symmetry at all. The next one we want to talk about, which also has a very specific type of shape, is the cubic, or the graph of x cubed. You'll notice in this case, it's kind of similar to the parabola, but it's a little bit skinnier, and it's like this left-hand side has been flipped downward. That's because when we cube negatives, we're actually getting negative values. So we're going to get this going down the y-axis. But the cubic graph is always going to have this very telltale sign of this S-curve. In this case, it's going all the way out to the left and all the way down, and all the way out to the right and all the way up. Even though it kind of looks like it's leveling out there at 2. It's not, it's just growing very, very fast. So domain and range here for the cubic graph is going to be all real numbers, or negative infinity to positive infinity. If we think about increase, decrease, and constant intervals, notice if we were riding this like a roller coaster, my arrow is increasing and still increasing. I know at the origin it looks like it's leveling out a little bit, but if we zoom in, you'll notice that it is still increasing there. It levels off never. And so we're going to be increasing this entire time from negative infinity to positive infinity. And you might notice in this case, since we have an x cubed, which is an odd exponent, well, if we took the lower left quadrant of this graph and rotated it about the origin, it would match up perfectly here with the top right quadrant. This means here that we have odd symmetry, and further proving that this is an odd function. The opposite of cubing is the cube root. And so we also want to make sure that we know this shape as well. Lucky for us, it has a very similar shape to the cubic graph, still having that S-curve, but just being turned sideways. For the cube root graph, we're still going all the way out to the left, and it's still growing down just a little bit more slowly. Same thing in the top right here, we're going to go all the way to the right, and it's still growing just a little bit more slow, since we're reversing the domain and range here. So domain and range for this cube root graph will still be all real numbers, or negative infinity to positive infinity. Same thing with the increase and decrease. Notice as we move from left to right, this graph is still increasing the entire time, never decreasing. So in this case, our interval of increase would be from negative infinity all the way to positive infinity, with no intervals of decrease or constant. And just like the cube graph that was odd and had odd symmetry, well, if we take this lower left-hand side or left-hand quadrant and rotate it about the origin, it's going to match up perfectly with the top right, making this graph also have odd symmetry. These are the 7 different types of parent functions that we need to have their characteristics and basic shapes known so we can use them to work with transformations. So let's just review them one more time. First off, we have the constant, which is just our horizontal line, the linear graph, the absolute value, which is our V shape, the quadratic, which is our parabola or U-shaped, the square root graph with no symmetry, our cubic, which is our S-curve, and finally, our cube root, which is our sideways S. Using these parent graphs and their basic shapes will help us be able to graph based on the function. Next, we're going to explore the transformations.